Hi everyone, in this lecture we will be discussing on different kinds of nuclear decay processes. First one is the particle decay. In this kind of decay, a radioactive nucleus or a unstable nucleus emits particles to become stable. So the particles could be alpha particle. Alpha means the nucleus of helium atom, or the particle could be a beta particle or generally electron or positron, or the particle can be a neutron. So this is example of particle decay where the emitted particles are alpha, beta or neutron. Now, there have another kind of decay process called radiative decay where the emitted one is not a particle, it's radiation. So, it's called radiative decay. When a excited or a nucleus at upper excited state will be become at lower state by emitting gamma radiation. So this kind of decay is called radiative decay. Now one simple question may arise in a nuclear reaction where there will be radiative decay and where there will be particle decay. So to know that, you have to consider the energy of excited state nucleus or radiative nucleus. Suppose the excited nucleus having energy 30 mega electron volt. In that case, this nucleus will emit particle. It's a probabilistic reaction. There could be also gamma radiation in case of giant resonance, but for our level we have to first consider if a nucleus having this much of energy, it will first decay some particle, generally alpha particle, and the nucleus will have low energy compared to initial. If the alpha particle get the energy 25 mega electron volt, the excited nucleus will have 5 mega electron volt energy. Point to be noted that this nucleus having 5 mega electron volt energy is not stable. To become stable, this will emit gamma radiation because it have no other option. If you remember, the binding energy per nucleon versus atomic number, the most of the nucleus is having energy 7 to 8 mega electron volt. So to emit a nucleon means to emit a proton or neutron from this excited nucleus. This nucleus must have energy greater than 7 mega electron volt. But in this case, it have only 5 mega electron volt. So it will not emit any particle. It will get stable after emitting radiation called gamma radiation, and finally it will become its ground state having energy 0. So that's how you can define where there will be a radiative decay and there will be a particle decay. Now we will be discussing on alpha decay, which one is a particle decay in nuclear physics or particle. Now first of all we will be discussing on alpha decay. So alpha is a particle which will be emitted when a nucleus, let's say it's a nucleus at its excited state, its proton number is Z and mass number is A, it will emit alpha particle. Alpha particle is nothing but having charge 2 and mass 4. So after emitting this alpha particle, this nuclei will have A minus 4 numbers of mass number and Z minus 2 of charge number. So this is an example of alpha decay. And now if you want to draw the energy of this emitted alpha particle with the particle yield, means the number of particles having certain energy that will be fixed, means any reaction, any kind of reaction having a alpha particle, that alpha particle's energy will be fixed for every single time, but due to the spectrometer or the device by which we will detect the energy of alpha particle, there will be a broadening of energy of emitted alpha particle. So this axis is the yield of alpha particle and this is the energy of emitted alpha particle. So it will be a constant fixed number, but due to the measuring device inaccuracy, different kinds of measuring device will measure some sort of error. So that error is denoted by this kind of spectral shift. This shift is due to the resolution of detector. So this is the spectrum for alpha particle, means it's a discrete energy spectrum. Now if you consider the beta decay, in that case we have, in beta decay we expect that the energy of emitted beta particle with yield number y must have the same discrete distribution. Means for beta decay, the energy of emitted beta particle should have the same energy. It was expected, but from experiment it was concluded that the emitted beta particle will have a continuous energy variation. So if this is the maximum energy that a beta particle can have, so this will be continuously varied by this kind of graph. You see, most of the beta particles having energy 0 and maximum particles will have average this kind of energy. So the extra energy carried by a particle called neutrino. So in beta decay, scientists assumed a particle called neutrino will take the other energy emitted from this kind of nuclear reaction. So in this case, the energy, that is the Q value, will be spreaded or will be spreaded by spreaded with the neutrino, beta particle and the daughter particle, that is y z minus or plus 1. For beta plus decay, this is neutrino, electron neutrino, and beta minus decay, this is anti-electron neutrino. So from this kind of experimental result, we confirm the existence of neutrino particle. Again, repeating this graph was expected, but experiment results suggest the energy of beta particles emitted during beta decay having this kind of continuous varying range, that is, the emitted beta particle not have a fixed energy for different time, means same reaction performed in different time will have different energies of beta particles. So and the extra amount of energy is assumed to be carried out by the neutrino particle. And now we will be calculating the energy that will be carried out by the beta particles. Now we will calculating the energy with so, carried out by beta particle. So for calculating the energy carried out by beta particle, we have to consider the equation which says the transition probability is lambda, which is equals to, this is the transition probability, means if the nucleus initially, this is the parent nuclei and it's have the initial wave function psi I, finally it produced daughter nuclei and the beta particle. The daughter nuclei having the wave function psi d, and initially the parent nuclei having the wave function psi p, and the transition between this state and this state's initial and final state is given by transition probability denoted by lambda, which is equals to 2 pi divided by h cross HIF square times dN by dEF. So this is the final state and this is the initial state. So the transition probability is dependent on the density of the state of final state. This state's density will decide the transition probability in this way, where this HIF is equals to integration of initial wave function, that's psi p star, times perturbation Hamiltonian times psi daughter integrated over entire volume of nucleus. So this is the HIF. Now to get this HIF value, we have to perform some sort of calculations. So we are doing the calculation after. So after that, we will be calculating this capital HIF. So again, write the our formula for transition probability lambda, that's equals to 2 pi divided by h cross mod square of HIF square times dN divided by dEF. Here we have to calculate this HIF value and dN by dEF value. First of all, we are going to calculate this HIF value. So our initial wave function psi I will be equals to psi of parent nuclei, and our final wave function psi f will be equals to psi daughter, and at final state we will get this is the initial state, this is the final state. In initial state we have the uh, parent nuclei, and in final state we have daughter nuclei, the beta particle and the neutrino. So the final wave function will be equals to psi d, psi beta and psi neutrino. Now to calculate this HIF, we have to put this psi I star here and psi f here. So HIF is not psi star p, it's equal to psi I star and psi f this. So if you put this psi I value from here and this psi f value from here, you will get HIF equals to integration psi I was psi p times H prime, this is perturbated Hamiltonian, times psi daughter, psi neutron, and psi beta integrated over d tau volume. Now we know the wave function for the psi nu and psi beta. So psi nu is equals to 1 divided by root v times e to the power p vector dot p vector is neutrinos p times r vector dot divided by h cross. This is the wave function for neutrino. To calculate this p nu, we have to consider the formula p nu square c square plus m naught m nu square c square is equals to the energy value, that is E mu square. Now if you consider the mass of neutrino, rest mass is 0 and energy of neutrino is 1, in that case you will get 1 square is 1, and here we have P nu square C square, so you will get P nu is equals to 1 divided by C, that's roughly equals to 10 to the power minus 2. So if you put this P nu here, we will get 1 divided by root V times e to the power, this P nu is 1 divided by C. So, and if you take the value of R is equals to 1, so we are assuming R equals to 1 Fermi. In that case, this will be equals to 1 times 1 mega electron volt times Fermi divided by Hc. So this is equals to 1 divided by root V times e to the power, Hc is nothing but 200 mega electron volt Fermi. So here mega electron volt Fermi and mega electron volt Fermi get cancelled, as exponential will have nothing power carried out. So finally we will get the wave function for neutrino is equals to 1 divided by root V times e to the power 1 divided by 2000. So as this 2000 is very large number and its exponential will be very small, so we will neglect this term, and finally we get this psi nu equals to 1 divided by root V. So we have to put this psi nu here and we have to get the value of psi beta in similar way. So the wave function equation of psi beta is equals to 1 divided by root V P of beta dot R divided by H cross, and for beta also the relativistic energy, that is P beta square C square m beta naught square C square is equals to energy of beta particle. Similarly, in this case the mass of beta particle is not equals to 0. This mass and speed of light squares give a result that mass of electron times c square equals to 0.511, I say, yes, 0.511. Remember this value 0.511, and if you put that value here 0.511 and take the value of E beta again 1, you will get P nu square C square equals to 1 minus 0.511, and finally P nu will be equals to we are calculating momentum for beta particles. So P beta c square equals to that, and finally the P beta will be equals to 0.86 divided by C mega electron volt. That's nearly equals to 10 to the power negative 3. In previous case we have shown this is 86. In previous case we have shown for the value of 10 to the power minus 2 p, we will get the psi nu is equals to 1 divided by root v. Similarly, in this case wave function for beta will be equals to e to the power beta, and this term will be neglected, and we will get psi beta also equals to 1 divided by root v. So finally we will get the HIF value, that is so psi beta is this, psi nu is this. So we have to put here it psi of parent time H prime dot psi of d into 1 divided by root v and 1 divided by root v d tau. So this root v will be get outside of this integration. 1 divided by v, and we will get some information about the psi p and psi d if we know the wave function, the particles, the parent and daughter nucleuses. So this psi p and psi d integration with perturbated Hamiltonian will give us the result 1 divided by v, that is as it is, and this whole term will give us a result denoted as MIV, and this MIV can be calculated if we know the wave function for parent and daughter nuclei. So we have to get the transition probability, we have to put this HIF value in this equation. So we are putting HIF from this equation to here. So you will get 2 pi divided by h cross, and this HIF is equals to MIV IF divided by V mod square times dn divided by del. Till now we have calculated the value of HIF, and now we have to calculate the density state, that is dn divided by def, and we will do that in our next lecture. Thank you for listening the lecture, and if you have something to say you can comment below. Thanks again.